Here is a combined summary of the 2 pages. Whole slide image, WSI, classification is a crucial task in computational pathology, which involves analyzing high-resolution images of tissue samples to diagnose diseases. Multiple instance learning, MIL, has gained popularity in this field due to its ability to learn from weakly labeled data, where only the diagnostic report is available, rather than requiring pixel-level annotations. However, MIL methods often suffer from the incorporation of redundant patches, leading to interference in the learning process. To address this issue, the authors propose an attention-based feature distillation multi-instance learning (AFD-MIL) approach. This method involves excluding redundant patches as a preprocessing step in weakly supervised learning, thereby mitigating interference from extensive noise. AFD-MIL uses attention mechanisms to distill features with high diagnostic value, as opposed to traditional practices of forcibly integrating all patches. Additionally, the authors introduce global loss optimization to finely control the feature distillation module. The authors highlight the limitations of existing MIL methods, which often focus on improving the feature fusion module but overlook the issue of redundant patches. They argue that AFD-MIL is orthogonal to many existing MIL methods, leading to consistent performance improvements. The proposed approach has achieved state-of-the-art performance on the Camelyon 16 and TCGA-NSCLC datasets, with accuracies of 91.47% and 93.33%, respectively. AFD-MIL involves constructing dual-channel feature distillation modules based on attention mechanisms and weakly supervised instance-level classifiers. These modules distill features from all original patches, eliminate redundant feature interference, and emphasize more valuable features. The distilled features are then transformed into WSI-level features through feature fusion for classification tasks. The authors also investigate the impacts of various model components on overall performance, including feature distillation scale, ablation experiments, and different distillation methods. The main contributions of this study are the introduction of dual-channel feature distillation as a preliminary control for selecting high diagnostic subregions in WSIs, the use of attention mechanisms to distill features with high diagnostic value, and the achievement of high interpretability and scalability. The authors demonstrate the potential of AFD-MIL for tumor detection and provide the code for further research. The AFD-MIL model, as depicted in Figure 1, is designed to improve the performance of multi-instance learning in whole slide images, WSI, by refining feature extraction and fusion processes. It utilizes a feature distillation module that includes 2 distinct channels: weakly supervised instance-level feature distillation and attention-based feature distillation. This dual-channel approach aims to enhance the model's ability to identify relevant features within patches, leading to more accurate WSI-level classifications. The weakly supervised instance-level feature distillation process, shown in Figure 2a in Algorithm 1, begins with segmenting a WSI into patches and extracting features using a pre-trained image encoder. The model then uses these features to predict the probability of each patch being classified as positive. The top highest predicted probabilities are selected for further processing, and the loss is calculated based on the WSI level label. This process enables weakly supervised learning of the patch classification network. In contrast, the attention-based feature distillation, presented in Figure 2b, focuses on identifying the most relevant patches within a WSI. By applying an attention mechanism, the model can weigh the importance of each patch's features, enhancing the accuracy of WSI-level classifications. The feature fusion and WSI-level classification process, detailed in Figure 2c and Algorithm 3, involves combining the refined features from both distillation channels. The fused features are then inputted into a classification network, which produces the final WSI-level classification results. The global loss optimization process is also presented in Algorithm 3, which integrates the losses from both distillation channels and the classification network, allowing for end-to-end training of the AFD-MIL model. Overall, the AFD-MIL model optimizes multi-instance learning in WSI analysis by introducing a dual-channel feature distillation approach that enhances feature extraction and fusion. The model's design addresses the limitations of traditional instance-level MIL methods, providing improved performance and interpretability in WSI classification tasks. The paper presents a novel weakly supervised learning framework for multi-instance learning, MIL, in digital pathology, which leverages both instance and bag-level labels. The proposed approach, named AFD-MIL, uses an attention-based feature distillation method to select the most relevant features from whole slide images, WSIs. This method is designed to improve the accuracy of WSI classification by identifying and fusing the most informative features. The AFD-MIL framework consists of three main components: instance feature extraction, feature distillation, and feature fusion. Instance features are extracted using a pre-trained ResNet-18 model. Feature distillation is achieved through two different algorithms. Algorithm 1, which uses a max pooling strategy to select the top features with the highest probabilities, and Algorithm 2, which utilizes an attention network to weight the instance features based on their relevance. The top features with the highest attention scores are then selected for further processing. Feature fusion is performed by combining the distilled features from both algorithms. A global loss function is introduced to optimize the feature distillation parameters, utilizing the WSI predictions to adjust the gradient backpropagation during training. This approach encourages the feature distillation step to favorably predict the final classification results. The authors evaluate their model on two publicly available datasets: Camelyon 16 for breast cancer metastasis detection and TCGA-NSCLC for lung cancer classification. The datasets are preprocessed by dividing the WSIs into 256 by 256 patches at 20x magnification, resulting in approximately 2.8 million patches for Camelyon 16 and 5.2 million patches for TCGA-NSCLC. The features are encoded using the ResNet-18 model pre-trained on ImageNet, and the same low-performance image encoder is used to highlight the superiority of the weakly supervised learning framework. The paper demonstrates that the AFD-MIL framework outperforms state-of-the-art MIL methods in both datasets, showcasing its potential for improving WSI classification accuracy in digital pathology. The paper discusses the application of attention-based feature distillation, AFD, in medical image analysis, focusing on the classification of tumor versus normal tissue in WSIs. The authors compare the performance of various MIL algorithms, including AFD-MIL, on two publicly available datasets, Camelyon 16 and NSCLC. The results show that AFD-MIL achieved the best performance in both datasets, with significant improvements over the original versions of AFD-MIL and Trans-MIL. The attention-based feature distillation module effectively mitigates the interference of redundant features, enhancing the classification performance. The study also investigates the impact of the number of features to be distilled, finding an optimal range for better performance. An ablation study validates the effectiveness of the proposed modules, demonstrating positive improvements in the classification task performance. The paper presents an ablation study to evaluate the effectiveness of various components in the proposed attention-based feature distillation multiple instance learning AFD-MIL framework. The results in Table 3 show that the combination of attention-based feature distillation and global loss optimization leads to improved performance on both Camelyon 16 and TCGA-NSCLC datasets. The feature distillation parameter K is shown to have a significant impact on model performance, as depicted in Figure 3. The authors also compare different feature distillation methods, including max positive and negative, and find that the latter is more effective for tasks involving classification of two subtypes of cancer. However, for benign malignant classification tasks, max positive is preferred due to its higher recall. The results are presented in Table 4. To visualize the effectiveness of the feature distillation module, the authors generate heat maps comparing the selected patches with the ground truth on the Camelyon 16 test set. Figure 4 shows a significant overlap between the ground truth and the region selected by AFD-MIL, demonstrating the ability of AFD-MIL to accurately capture tumor features in pathological images. The proposed AFD-MIL framework is a novel orthogonal MIL methodology that significantly enhances whole slide image classification performance. By identifying the most important patches in WSI, AFD-MIL eliminates redundant features and provides finer-grained guidance for the learning process. The framework achieves state-of-the-art performance on both breast cancer and non-small cell lung cancer classification tasks and exhibits excellent interpretability. Its compatibility with other models makes it highly scalable and suitable for clinical diagnostic assistance, providing fresh insights into the MIL problem. This research paper focuses on the application of deep learning techniques in computational pathology, specifically in whole slide image analysis. The authors acknowledge the support of various grants and funding agencies. The paper provides a comprehensive review of existing literature in the field, citing 36 references that explore various aspects of whole slide image analysis, including image compression, segmentation, and classification. The references highlight the importance of deep learning in computational pathology, including the use of convolutional neural networks, CNNs, and attention-based models for image analysis. The authors discuss the challenges of analyzing whole slide images, which can be gigapixels in size, and the need for efficient algorithms that can handle such large images. They also highlight the importance of weakly supervised learning methods, which can learn from limited annotated data. The paper cites various studies that have applied deep learning techniques to whole slide image analysis, including the use of multiple instance learning, MIL, frameworks, which can learn from bags of instances, and attention-based models, which can focus on relevant regions of the image. The authors also discuss the importance of data augmentation, transfer learning, and ensemble methods in improving the performance of deep learning models in whole slide image analysis. They highlight the need for further research in this area, particularly in developing more efficient and accurate algorithms that can handle large images. Overall, this paper provides a comprehensive review of the existing literature in whole slide image analysis, highlighting the challenges and opportunities in this field, and the importance of deep learning techniques in advancing the field of computational pathology.